I've finally gotten around to writing the programs and making the video that will show how to make a few embellishments on bisection and Newton. This will go along pretty nicely with what we're going to talk about in one of our classroom discussions, so this should be alright. Firstly, I still have the bisect.f90 and new.f90 programs from before. Obviously, bisect does the method of bisection. New.f90 does Newton's method. Both are done in this very simple way that we had talked about previously. So to begin with, let's look at the bisection code. Now, I've also made the font much bigger so that it won't be so difficult to read. We have a program statement, program bisect, real, colon, colon, no spaces between the colons, a comma b comma m comma f. Just like before, a and b are the beginning and ends of our initial interval. They'll get overwritten as we go along. M will represent the computed midpoint. F is the name of the function that we wish to find a zero of. As before, I'm going to use the x cubed minus 3 function as my example. If you'll recall, the interval from 1 to 2 was a satisfactory beginning interval. The function values at 1 and 2 had different signs, so this was the generic setup for bisection. The first thing I want to take care of is this. We showed that as A and B come together, potentially you could have a real problem calculating the midpoint like this. In fact, we showed in an example that it's conceivable that the computed midpoint is not actually between A and B because of floating point round-off error. So I'm going to alter the way that I calculate the midpoint. Instead of just averaging them, we're going to have A plus B minus A over 2. I'm going to take the beginning part and add half of the width of the interval. We saw by using algebra that this is equivalent to A plus B over 2 mathematically, but it is not numerically. In this case, as we compute along, A minus B, B minus A, should be getting very small. Typically, A isn't 0, so eventually the m's will stop changing, and they'll all be the A, the left end of the current interval. When that happens, it's a signal to us. It's a signal that because of numerical rounding properties, we should stop computing because the midpoint isn't changing anymore. We'll put in a test for that in a moment also, but as always, I want to see that my code actually does what it's supposed to do. So I'll save that. I quit out to the operating system. I compile my program and run it. If you compare these numbers with what we got the other day, they're obviously the same numbers. The calculate the midpoint by averaging things wasn't yet causing any trouble. It might well never have caused any trouble, so naturally we get the same answers. Let's look at the next little embellishment that we could have. So I'll clear this so the screen isn't so messy looking. We'll look at our program again. During an in-class discussion, we mentioned that this is not a very good way to test if f of a and f of m have opposite signs. If we were doing exact arithmetic with no rounding errors, then there would be no trouble. But in our floating point system, there is only a finite number of floating point values, so there's a smallest positive one. If f of a and f of b were both small in magnitude, it's entirely possible that f of a times f of b would evaluate to 0 even when it should be negative. That could cause the wrong clause in the if-then-else statement to get executed, so this is not good. There's a couple of ways I could think about fixing this. Probably the most straightforward one is to make up a new function that I'll call check sign or something like that. Check sign is going to decide if f and a and f of m have opposite signs, but it's going to do it in a manner in which no underflow can happen. So I'm going to have a new thing. I'm going to have an integer function, and I might as well go ahead and put it in my program. Integer check sign. Check sign is going to receive a floating point number, and we're going to use some logic or the other to decide whether or not the number is positive or negative. Function check sign does not need to know that I'm sending it a value of the f function. So I'm just going to make up some nondescript name. I'm going to send check sign a value. Now, secretly, of course, value is going to be f of a or f of m, but check sign doesn't need to know that. We have to do our usual declarations. Force of habit, we have no real numbers here. Well, actually, we do. So I need to put in everything my function will need, which is, in this case, not very much. We're sending it a real number, a number of type real in the floating point system, that is. Now, just at the moment, I'm going to be completely naive about the possibility that that thing might have evaluated to 0. We'll put in a check for that too later. So for right now, I'm going to pretend that my value is positive. So I'm going to say check sign is 1. Now, either that's true or it's not. If it's true, then I'm done with my thinking. And if it's not, I need to make check sign negative 1. And this is all that I'm going to do. Now, as I always like to do, I'm going to make sure that this compiles before I actually try to run it to make sure that I haven't made any typographical errors or anything. I'll feed it back through the compiler. There are no syntax errors. Of course, that doesn't mean my code is right, it just means there's no typos in it. No typos that would cause the compiler to complain anyway. So here's what I'm going to do. I'm not going to multiply f of a and f of m together. Instead, I'm going to multiply check sign of f of a and check sign of f of m together, because these are integers now. Check sign sends back either a 1 or a negative 1. If they're both the same sign, when you multiply 1 times 1 or 1 times negative 1, you'll get 1 back again. If they're opposite signs, one of them will be 1, the other one will be negative 1. Multiply them together and get negative 1. So there's no possibility for underflow. An interesting thing, I should not leave that as 0.0 because check sign doesn't give floating point values. If a compiler was really picky, it would complain about that. I like that a lot better. And the numbers that I get are apparently the same numbers I had before, so these precautions are not strictly necessary for the one little problem that we're looking at right now, but as a general philosophy, this way of doing things is better. So we have fixed up the way we calculate the m. We have removed the possibility of an underflow in the f of a times f of m calculation. One thing that we haven't checked is the possibility that we may somehow miraculously have landed on a number that the function value f evaluates to 0. If you go and you look in check sign, on entry, I assume that check sign is going to be 1. That corresponds to value having a positive value. And then I check and see if value is less than 0, 0.0, in which case I set check sign equal to negative 1. I need to put in some sort of code that's going to look at the possibility that the value might actually be 0. There's a lot of different ways you could code this up. At the moment, I'm just wanting to be as simple as I can, so I'll just put another if in. We could do if, then, else ifs also, but we'll save that for another time. If the value is exactly 0, which is unlikely looking but could happen, how shall I represent this? I'm talking integers here, so positive 1 indicates that value is positive, negative 1 indicates value is negative. I'll do this. If the value that I'm feeding into check sign actually evaluates to 0, exactly 0, then I'll make the integer value of check sign 0. We'll be able to detect this in our main program. But as usual, make sure that it compiles and runs still. Now in my main program, I can see if the product of these two check sign FA, check sign FM numbers is now positive, negative, or 0. So let's do this. So I need to figure out how I'm going to incorporate this in my main program. I could do this a lot of different ways, but I'm going to try to be as straightforward about it as possible. I'm going to make up another integer variable. I'll call it decide. Decide is going to be the product of these checksum quantities. So, being as lazy as I can humanly be, I will copy and paste. I'll go up before I do this business. And I will paste that in. Now, before I do anything else, I'm going to fix up my program now, just as it is, to use variable decide in deciding what happens. Now, I haven't changed the logic any, I've just changed the organization slightly. I'm wanting to do this so I don't have to keep typing check sign f of a and check sign f of m and so on and so forth. Let's see if we made any syntax errors. We did. This is why it's good to check these things. I have that extra parentheses that I forgot to get rid of. And again, we get the same sort of numbers that we were getting previously. Since everything worked pretty much the same as it did before, I'm happy with this. If decide is not 0, then that logic is exactly the logic we've been doing, and everything's fine. All I've got to do is to decide what I should do if decide does come up 0, which may be unlikely, but conceivably could happen. I could go on and use the if then else if, but I'm just going to put it in two clauses here. If decide is exactly 0, which is the thing that's going to determine whether or not I've landed on the solution, then I'm going to have an end if, of course, and I'm going to put in some stuff that indicates to the programmer or user that we're not going to continue calculating. If this happens, then, well, I'm going to explain to the user what's happened. And then, rather than just stop, I'm going to print out the things that made me decide this. That is to say, the A, the M, the f of A, and the f of M. I'll put a character string in. To explain what it is that I'm printing out. Then I'll print out A and M and f of A and f of M. Not only that, but because of what we've been doing, I expect that in the end, that the computed midpoint is going to be the same as the left end of the interval. So I'll indicate the difference between M and A. In exact arithmetic, that would be a positive number, but eventually I expect to get a 0 out of it. And out of a sense of paranoia, I'll print out b minus m. This should be a positive number as well. Then I'll back up and fix that syntax error that I just committed. Now, if this happens, logically speaking, I'm done. It would be useless to continue calculating. So if this clause happens, I'll print out that I'm going to end the program run. And to end, I don't say end. That would mean the end of the main program unit, which is not what I want to do. I say stop. Let's see if we made any syntax errors that we didn't catch. Apparently not. Same numbers as before, of course. Now that we've put in some checks, I think it might be instructive to increase the number of steps. So instead of just doing I equal 1 to 10, I think I'm going to do I equal 1 to 50. When I run this, I'll pipe it through less so it doesn't scroll off the screen on me. As you can see, the m, the f of x, the computed midpoints are getting close to 1.91293108. The function value that goes with it is 9 times 10 to the minus 7. We continue, and you'll notice that the function value isn't changing anymore after a while. Let's back up until we see some changes. That's the last one that was different. No, wait, there's 108 at the end. Then it's 120s all the way down. None of my safety checks have triggered here yet. So what's happening is the clause that would decide to stop because the function value's signs multiplied to 0, it never gets executed. That isn't a big surprise. We never really thought it was likely to do that anyway. Another thing that we haven't done is we haven't checked to see if the midpoint and the old right end or the midpoint and the old left end are the same or not. So I'll put in a check for that too. I'll do this right before I do the decision part. So we've already calculated the new m. We still have the old a and b. And again, I'm not going to be very sophisticated in my programming statements. If a as a floating point number is exactly equal to m, then, and I'll put an end if in. Now, textbooks and some compilers even will warn you that you should not compare two floating point numbers for exact equality, and they're quite right. Usually, if you do that, rounding errors will mess you up, but you see, that's what we're up to here. I suspect eventually that a and m are going to be the same number in my computer, and I want to check for that. Print star, comma, ASCII string at step I, a is the same as m. Now, if that happens in the current setup, I'm done computing. I don't have to do anything else. Stop. End if. It's conceivable, not likely, but it's conceivable that A might be M, or it's conceivable that B might be M. Out of a sense of paranoia, I'll check for that too. So I'm slowly putting in all of these checks and balances to catch everything that we've thought about so far that could conceivably go wrong with our program. Let's see. As always, it's possible I've made some typos and syntax errors. Nothing serious enough for the compiler to complain about. At step 24, the computed B and the computed M are the same. There is no sense in going forward. If I want to make my test a little bit more sophisticated, I want to detect even that possibility that I jumped outside the interval. How could that be? When I compute the new midpoint, if A is bigger than or equal to the midpoint, then we've jumped outside the interval to the left. If B is less than or equal to the computed midpoint, then I've jumped outside to the right. Oh, I have to fix what I'm printing out here. This would mean that A was bigger than or equal to M, so we'll catch that too. And at step 24, B is less than or equal to M. I've made a typo in my ASCII string that I'm putting out. It doesn't have any effect on the code, of course, but it makes it look very odd. I'll put some spaces in so that it looks nicer. So we're printing out decide, the computed midpoint, the function value that goes with that midpoint, until we get to step 24, where B is less than or equal to M, meaning that the M has actually either been equal to the B, which in this case is what happened, or actually is bigger than it, and once that happens, we stop computing. I've been meaning to upload this for several days now, but I keep getting interrupted. I'm going to have to do some editing on this video itself because of interruptions. I think if you look at it, you can see how to put in similar sorts of safety checks on Newton's method. If not, I'll make another video about that pretty soon. I hope everyone's having a good day, has a good weekend, and I'll talk to you again soon.